At the Longevity Escape Velocity Foundation, sometimes referred to as LEV Foundation, or just LEVF for short, a primary question always under consideration is, how might we extend healthy human lifespans? Well, in 2021, we decided to try to answer this question by first asking, what has worked in rodents, that is, in mice and rats? You see, there have been hundreds of scientific studies on rodents that reported that a particular intervention successfully extended lifespan. In 2021, the LEV Foundation President and Chief Science Officer Dr. Aubrey de Grey decided that LEV Foundation should try to find all studies that reported successful lifespan extension in rodents and put that information into a central location. So, we did that. It looks something like this. Dr. de Grey thought this information might be very useful because many people in the longevity research field have been wondering, if lifespan extension can be achieved in rodents with single interventions, would more lifespan extension be possible if we combined previously successful interventions? So, LEV Foundation researchers used the rodent lifespan extension data to plan experiments in mice using a combination of treatments, each of which had been reported in a previous study to extend rodent lifespan. These combination experiments are LEV Foundation's Robust Mouse Rejuvenation Research Program, abbreviated RMR. In that program, LEV Foundation researchers used the large data set of lifespan studies mentioned earlier to help them choose which interventions, if used in combination, might reasonably result in much longer-lived mice. And they hoped the findings from this program could translate to humans, resulting in healthy, longer-lived people. As of the end of 2025, LEV Foundation has actually finished its first RMR study called RMR1 and is in the process of planning and performing pilot studies for RMR2, the second iteration of the program. You can read more about the RMR program at LEV Foundation's website, levf.org. But what about all that study data about successful life extension interventions in rodents that LEV Foundation uses to design its RMR experiments? At the beginning of the RMR1 study, this data was just sitting in a private spreadsheet. LEV Foundation decided it would be a good idea to make this data set available to the public so other researchers could use it in their research and experimental designs. So they built a software tool that enables users to search and sort this study data about lifespan extension experiments in rodents. It looks like this. They decided to call it the Rodent Aging Interventions Database, or RAID for short. It's freely available at LEV Foundation's website, levf.org/RAID. If we scroll down a bit, you can see some of the data in the database is currently sorted and displayed by the magnitude of effect that a given intervention had on the average lifespan, which includes data of both mean and median lifespan. But you can also rank and visualize the data by the magnitude of the effect that each intervention had on maximum lifespan. The visualization of the lifespan extension effect is shown in the horizontal bar chart below. The length of each bar represents its magnitude of lifespan extension relative to the other interventions currently being visualized. The details of each experiment, such as the intervention name, age of onset, abbreviated AO, number of days of lifespan extension, abbreviated LE, and the percentage increase in lifespan relative to the control group in that particular study, are written on each bar in the chart. You can also search for specific interventions using the intervention search field there at the top. For example, if you type rapamycin into the search bar, the results down below are immediately filtered such that only studies with the word rapamycin in its intervention name are illustrated in the bar chart. Note that the pink bars represent the results of tests in female rodents, blue bars represent the results of tests in male rodents, and purple bars represent the results that were analyzed with data from both males and females combined or pooled in the statistical analysis. Gray bars are for the rare study that apparently didn't report the sex of the animals used in the experiment. Another useful feature of this tool is the ability to click on any entry to display the details of the study. For example, if we click on this top bar, this pink one, then scroll down, a table appears below the bar which contains many essential study characteristics and findings. This feature works for any of the bars in the bar chart. If we scroll back up, there's one more feature I'd like to show you. And that feature is the ability to filter the data that appears in the chart using other study parameters, including the age of onset of the intervention, the type of intervention, such as pharmaceutical, genetic, or dietary, the sex of the rodents in the case you want to examine study results in a particular sex, and the number treated in the case the study size is of particular interest to you. Give it a try for yourself. Again, the URL as of December 2025 is levf.org/RAID. The RAID database creation effort and some of its noteworthy findings are described in a manuscript published in early 2025 in the journal Aging, Albany, New York. You can find it in PubMed under the PubMed ID 40156933. At the time of the publication of this manuscript, RAID included 121 unique studies. But throughout 2025, I have added an additional 62 studies for a total of 183 unique studies currently in the dataset. And I have a list of about 40 more studies under consideration for inclusion. I'm the first author of this manuscript, Maximus Peto, the Chief Science Monitor for LEV Foundation, and the creator and narrator of this video. I performed most of the screening of the scientific literature to find studies to include in RAID, extracted the data from the research reports, and wrote the primary manuscript draft. The second author, Anthony Floyd, created the software tool you just saw using JavaScript. The third author, Ben Zealley, is the Director of Web Services and Content at LEV Foundation. Ben adapted Anthony's software tool for use on the web and enhanced its user interface. He also created the RAID name and the logo. And the final author, Dr. Aubrey de Grey, is the President and Chief Science Officer of LEV Foundation. He initiated this project for use by the Foundation in designing RMR experiments. If you have any suggestions for RAID or would like to nominate a study for inclusion in our dataset, you can email us at raid@levf.org. This concludes the introduction to the Rodent Aging Interventions Database. If you like this kind of work, you can make more of it happen by donating at LEV Foundation's website, levf.org/donate. Thanks for watching.
The Rodent Aging Interventions Database, RAID, a data visualization tool for all studies reporting rodent lifespan extension, a research paper authored by Maximus V. Peto, Anthony J. Floyd, Ben Zealley, and Aubrey D.N.J. de Grey. Published in Aging Magazine in 2025, Volume 17, Number 3. The institutional affiliations of the researchers are Long Life Labs, LLC in Buffalo, New York, and the Longevity Escape Velocity, or LEV Foundation, based in San Francisco, California. Correspondence regarding this paper may be addressed to Maximus V. Peto, whose email address is maximus@longlifelabs.com. This paper was received on July 23, 2024, accepted for publication on March 18, 2025, and published on March 27, 2025. This paper is copyrighted in 2025 by Maximus Peto and the other researchers. This is an open access article distributed under the terms of the Creative Commons Attribution License, CC BY 4.0, which permits unrestricted use, distribution, and reproduction in any medium, provided the original author and source are credited. This audio version of the paper is read by Gennady Stolyarov II. Abstract. Numerous studies have investigated the effects of various interventions on the lifespans of mice and rats. The design of future rodent lifespan extension experiments might consider experimental parameters used in earlier investigations, but finding and reviewing all previous experiments requires a substantial resource investment. Additionally, when studied collectively, the results of previous investigations might suggest fundamental mechanisms causing age-related degeneration. Here, we report our efforts to find and aggregate data from all research reports of lifespan extension in mice or rats, which we call the Rodent Aging Interventions Database, RAID. We identified studies for inclusion using complex PubMed queries and by nomination from our colleagues in the field. The relevant data from each study was manually extracted and recorded in a table. A publicly available web-based software tool was then created to enable users to visualize and filter this data in a convenient manner. Our current data set, covering publications up to October 2022, includes 121 unique studies reporting on 212 distinct intervention protocols that extended lifespan in mice or rats. We intend to periodically update our data set as new rodent lifespan studies are reported. RAID is publicly available at https://levf.org/RAID. Introduction. Rodent lifespan extension has been studied for decades. Complicating the analysis of this data is its heterogeneity regarding species, strain, sex, intervention type, genetic, dietary, pharmaceutical, etc., age at administration, etc. We imagined several valuable outcomes described below, which might result from aggregating this data and making it publicly available, easily navigable, and visually ranked according to the magnitude of lifespan extension reported. Enhance conceptual thinking about causes of age-related degeneration and mortality. Currently, there is no consensus among scientists about the ultimate causes of age-associated degeneration and increased mortality. Many different contributors to these phenomena have been explored, including accumulation of DNA damage, telomere shortening, accumulation of molecular and cellular damage in and around cells and tissues, a rise in the prevalence of senescent cells, genetic quasi-programs, and mitochondrial free radical generation, among others. Causal theories of age-related degeneration and increased mortality must explain not only why these age-related phenomena occur, but also why certain interventions and not others extend lifespan. If sufficient data about life-extending interventions can be accumulated and evaluated as a group, one might be better able to infer the underlying mechanisms by observing shared characteristics among interventions reported to extend lifespan. For example, to the casual observer, several seemingly unrelated interventions have been reported to extend rodent lifespan, including knockout of type 5 adenylyl cyclase, AC5, knockout of pregnancy-associated plasma protein A, PAPPA, and surgical removal of the pituitary gland. However, each of these interventions were also reported to interfere with the growth hormone insulin-like growth factor 1, GH-IGF-1, signaling axis. Interference with this pathway has been noted to extend lifespan in earlier studies, such as was observed in Ames dwarf mice, and growth hormone receptor knockout, GHRKO mice. When viewed together, considering how GH-IGF-1 are related to growth during development, these results support the idea that events and circumstances associated with development might fundamentally affect an organism's lifespan. Facilitate efficient planning of rodent life extension experiments. When deciding on the parameters of a pending rodent life extension investigation, it can be cumbersome to identify all literature relevant to the interventions under consideration. For example, rapamycin has been reported to extend rodent lifespan in multiple studies, but the details of administration have varied and include 126 parts per million in food, 14 parts per million in food and combined with metformin, 42 parts per million in food, 8 milligrams per kilogram injection, and 14.7 parts per million combined with acarbose. We designed our data visualization tool to be capable of quickly and easily searching for all studies using an intervention keyword. It is our hope that this tool will enable other researchers to more efficiently locate earlier findings which are relevant to their contemplated rodent lifespan experiments. Help clarify misunderstandings about rodent life extension research. There appear to be significant misunderstandings about the state of life extension research, some of which might be caused by inaccurate or misleading reporting on scientific studies. For example, the headline of an article by CNN Health on January 12, 2023 read, quote, "Old mice grow young again in study. Can people do the same?" End quote. The focus of that article was the report about the creation of a system the authors called, quote, "inducible changes to the epigenome," end quote, or ICE. This system was apparently created in part to evaluate the extent to which age-related epigenetic changes are associated with age-related alterations, and to help corroborate the author's, quote, "information theory of aging," end quote. Importantly, no magnitude of mouse lifespan extension was mentioned in the CNN article, even though the title of the article implies life extension by using the phrase, "old mice grow young again." Sensational or hyperbolic titles of popular science articles might create misunderstandings about and unrealistic expectations for near-term prospects for human lifespan enhancement. We believe that such misconceptions might be less frequent or more easily corrected, given the existence of a reliable, manually verified, publicly available source of all scientific studies of successful rodent lifespan extension. Such a resource could help engender more accurate understanding about the current state of life extension research and thereby facilitate more realistic expectations about the near-term prospects for human lifespan enhancement. There have been multiple efforts to aggregate data about aging and lifespan in various animals. Among these include the Healthy Worm Database, which accumulates data on lifespan extension experiments in Caenorhabditis elegans. Another resource, Human Aging Genomic Resources, HAGR, includes multiple databases on topics such as animal life history data and molecular signatures of dietary restriction. And AgeMeta is a database of mammalian gene expression during aging. However, we were unable to locate a comprehensive database of mouse and rat studies that reported statistically significant lifespan extension. Motivated by the unique advantages that might be gained from a public database focused on rodent life extension, we have created the Rodent Aging Interventions Database, RAID, a curated set of intervention studies reporting lifespan extension in rodents with an accompanying data visualization software tool that is publicly available on the internet. We anticipate that RAID will enhance the ability of researchers to analyze the many studies of rodent lifespan extension and make inferences about the underlying mechanisms causing age-related degeneration and increased risk of mortality. Results. Our PubMed queries used to find the studies to construct RAID resulted in a total of 1,677 studies to be evaluated for relevance according to their titles. Manual evaluation of these resulted in retaining 292 abstracts for subsequent evaluation of their manuscripts. The evaluation of those manuscripts, when combined with relevant nominations by authors and other colleagues, resulted in 121 unique studies being included in the final dataset, which included 212 distinct intervention protocols. Due to variation between lifespans of control groups in different rodent experiments, the percent of lifespan extension reported can be misleading. For example, an extension of 10% in median lifespan relative to a control group with a median lifespan of 800 days is equivalent to a 13.3% lifespan extension relative to a control group with a median lifespan of 600 days, 80 days of life extension for each. Therefore, in the RAID data visualization tool, lifespan extension is sorted in descending order according to the number of days of lifespan extension reported relative to controls, rather than the percentage of extension. The mean or median, hereafter mean/median, lifespan extension in our data set ranges from plus 18 days in male Fisher 344 rats administered 300 milligrams per kilogram per day of metformin to plus 930 days in male Y-star rats administered 1.7 milligrams per kilogram body weight of C60 fullerene in olive oil multiple times via oral gavage. Maximum lifespan extension in our data set ranges from plus 28 days in female Het3 mice administered acarbose at 1,000 parts per million in food to plus 870 days in male Y-star rats administered 1.7 milligrams per kilogram body weight of C60 fullerene in olive oil multiple times via oral gavage. The RAID data visualization tool is publicly available at https://levf.org/RAID. Figure 1 is an image of the tool in a web browser. Our data set yielded noteworthy observations. Firstly, omitting the as yet to be replicated C60 fullerene study, the 5 greatest median lifespan extension outcomes, plus 447 to plus 625 days, all occurred in females. Secondly, 9 of the 10 most effective interventions, plus 346 to plus 625 days, included either calorie restriction or interference with the GH-IGF-1 pathway, primary pituitary deficiency, GHRH knockout, and PIT1 mutation. Excluding the C60 fullerene report and studies using either calorie restriction or GH-IGF-1 interference, the 3 most effective interventions in each sex are presented in Table 1 and discussed thereafter. This is Figure 1, the RAID data visualization tool. The header reads Rodent Aging Interventions Database, Data Visualization Tool. RAID provides a visual representation of the extension in lifespan achieved during published interventional studies in normally aging rodents, mice, and rats. For more information on the project's background and scope, click here, which takes one to this present paper. One is able to display and sort by extension of average lifespan or maximum lifespan. The filters include intervention search, age at onset, intervention type, sex of rodents, number treated. The sex key includes options for females, males, pooled or not reported, and then one is able to click on any entry to display details of the study, including age at onset, marked AO, and lifespan extension, marked LE. Table 1 shows the 3 most effective interventions for each sex. Footnote A reads, these are the interventions with the largest increase in lifespan in days in our data set after excluding studies about calorie restriction, GH-IGF-1 interference, and the exceptional C60 fullerene study. For females, with regard to mean/median life extension, the most effective intervention is at plus 270 days with VEGF overexpression from birth. The second most effective intervention is for plus 239 days with 14.7 parts per million rapamycin in food, and 1,000 parts per million acarbose in food starting at 9 months. The third most effective intervention is at plus 204 days, with 14 parts per million rapamycin in food and 1,000 parts per million metformin in food starting at 9 months. For females, with regard to maximum lifespan extension, the most effective intervention is at plus 300 days with VEGF overexpression from birth. The second most effective intervention is at plus 218 days with 14.7 parts per million rapamycin in food and 1,000 parts per million acarbose in food starting at 9 months. The third most effective intervention is at plus 186 days, with 14 parts per million rapamycin in food and 1,000 parts per million metformin in food starting at 9 months. For males, the three most effective interventions for mean/median lifespan are the following. The most effective intervention is at plus 360 days with VEGF overexpression from birth. The second most effective intervention is at plus 263 days with 14.7 parts per million rapamycin in food and 1,000 parts per million acarbose in food starting at 9 months. And the third most effective intervention is at plus 255 days with 24-hour fasting every other day for 3 days per week starting at 20 weeks. For males, the three most effective interventions for maximum lifespan are the following. The most effective intervention is at plus 405 days with 10 grams per liter of N-acetylcysteine in drinking water starting at 7 months. The second most effective intervention is at plus 400 days with 5 grams per liter of N-acetylcysteine in drinking water starting at 7 months. The third most effective intervention is at plus 345 days with VEGF overexpression from birth. Referring to Table 1, note that overexpression of vascular endothelial growth factor, VEGF, ranks in the top 3 for both males and females in median lifespan extension, and for males in maximum lifespan extension. Because this intervention may be operating via a different mechanism of action compared to more popularly discussed interventions, dietary restriction, GH-IGF-1 interference, metformin, rapamycin, and senolytics, we suspect VEGF overexpression may be particularly interesting for further research. Additionally, note that while N-acetylcysteine in drinking water has a high-ranking intervention in males for maximum lifespan extension, it had no significant effect on median or maximum lifespan in females. This suggests that in late life, male and not female mouse lifespan may be limited by redox-related degeneration that is substantially alleviated by dietary N-acetylcysteine, and that most of the positive effects might be achieved at a dose of 5 grams per liter of drinking water or lower. Finally, we note that rapamycin with acarbose was among the top 3 interventions for both male and female mice, suggesting that this combination may have significant and consistent benefits regardless of sex. Unfortunately, key data and statistical information were missing from a substantial number of our selected studies. For example, 11 of 121 studies, 9%, appeared not to report the number of rodents in the treatment group, and 21 of 116, 18%, did not report specific p-values for their findings on mean/median lifespan. Approximately 25% of studies did not explicitly report the numerical value for lifespan in days for treatment and control groups, and those figures had to be estimated from survival curves. The number and proportion of studies apparently missing essential data are reported in Table 2. Discussion. Our original data table contains primary data from selected studies published through October 2022. We intend to periodically update our data set by 1. Using refined and expanded PubMed queries to identify studies that our initial queries missed, and studies that have been published after October 2022. 2. Using machine learning algorithms trained with our initial dataset to identify other candidate studies in the literature. And 3. Considering studies nominated by others. If readers have reviewed our RAID visualization tool in detail, including the list of pending inclusions provided at https://www.levf.org/projects/RAID #about, and are aware of a relevant study that we appear to have missed, we invite them to nominate that study for inclusion by emailing us at raid@levf.org. Future additions to our dataset will also include data from studies which investigated a possible life extension effect in rodents but failed to observe one or observed negative effects. Furthermore, data from studies using other rodents such as guinea pigs, gerbils, squirrels, chipmunks, and naked mole rats would also be appropriate for RAID. But we did not perform targeted queries for these species for the version reported here. If other investigators are interested in collaborating with us to expand the dataset, we invite them to email us at raid@levf.org. Table 2 shows the number and proportion of studies missing essential information. In regard to the statistical parameter of number of controls, the number of studies missing is 12 out of 121. That is 9.9% of studies missing. In regard to the statistical parameter of the number treated, the number of studies missing is 11 out of 121. The percentage of studies missing is 9.0%. With regard to the p-value for mean/median lifespan, the footnote clarifies the denominator is the number of studies which reported an effect on mean/median lifespan in the treatment group relative to controls. Studies reporting no effect on this parameter were excluded from this calculation, and in this case, the number of studies missing is 21 out of 116. The percent of studies missing is 18.1%. With regard to the p-value for maximum lifespan, footnote B clarifies that the denominator is the number of studies which reported an effect on maximum lifespan in the treatment group relative to controls. Studies reporting no effect were excluded from this calculation. The two denominators differ: 105 for the p-value for maximum lifespan versus 107 for the definition of maximum lifespan, because some studies gave a definition for maximum lifespan but did not report a significant effect on it, and those were excluded from the denominator for the studies expected to report p-values for maximum lifespan extension. So, for the p-value for maximum lifespan, the number of studies missing was 62 out of 105, or 59.0%. For the definition of maximum lifespan, the number of studies missing was 35 out of 107, and that constitutes 32.7% of studies missing. In regard to the explicit report of lifespan in days, footnote C states, this refers to studies for which numerical lifespan data was not reported in the text, and estimation was required from the reported survival curves. In this regard, the number of studies missing was 30 out of 121, and the percentage of studies missing was 24.7. Given that our current data set is based on searches extending only up to October of 2022, we did consider bringing the collection fully up to date using the original search strategies described herein before submitting this manuscript for publication. However, we are also working on improvements to our data collection methods, which we plan to implement in our next batch update. Particularly, we are in the process of developing machine learning algorithms to identify relevant studies for RAID using our existing dataset as true positives to train software to identify other candidate studies for inclusion. We intend to use these algorithms to search both PubMed and the wider internet for relevant studies. This is in addition to the new PubMed query phrases we have developed since our initial screen, based in part on analysis of the existing dataset. These methods will be applied not only to the years 2022 to 2025, but to all publication dates. We expect these techniques to substantially expand our dataset, but as they will require significant additional time and effort to implement, we intend to introduce them in a batch update to RAID before the end of 2025. After that point, maintaining RAID's currentness should require relatively little time investment. Missing data significantly limited the types of evaluation which could be conducted. For example, the web-based data visualization tool does not include the ability to filter by p-values, since nearly 20% of median lifespan data and nearly 60% of maximum lifespan comparisons were not accompanied by p-values. Relatedly, a fundamental caveat about our dataset is that approximately 25% of lifespan figures in these studies had to be manually estimated from survival curves because exact data could not be found in the associated manuscripts. To enhance meta-analysis of lifespan extension studies and promote efficient data collection, we humbly suggest that investigators provide a minimum set of essential study parameters and statistical information in all future publications. Data aggregation and summary analysis is more efficient when these parameters are published clearly and precisely. Furthermore, given advancing machine intelligence, access to this data in an easily searchable format will allow for new methods of aggregation and analysis. We present our suggestions for minimum essential data for all future rodent life extension investigations in Table 3. Table 3 displays the suggested minimum essential data for rodent life extension investigations. In regard to study parameters, the table suggests including 1. Species, 2. Strain, 3. Sex, 4. Genetic modifications, 5. Intervention, dose, and route of administration, 6. Age at initiation of intervention, and 7. Numbers of living uncensored rodents in all control and treatment groups at each point of comparison. In regard to lifespan effects, the table recommends including 1. Lifespan in days at 90% survival, 50% survival, and 10% survival for control and treatment groups, and 2. Survival curves of each treatment group and its control group in a single figure. In regard to statistical information, the table recommends including 1. Specific p-values for comparisons of lifespan at 90% survival, 50% survival, and 10% survival for treatment groups relative to controls, regardless of significance. 2. The type of statistical test used to assess the above comparisons. For example, Fisher's exact test and Boschlew's test. 3. Definition of maximum lifespan if something other than lifespan at 10% survival is used. For example, average lifespan of the last 2 rodents. And 4. The log rank test and its associated p-value for the comparison of the survival curves of the treatment groups compared to their control groups. Furthermore, the table recommends to publish raw lifespan data, lifespan in days of each mouse in all control and treatment groups, for example, in a supplementary data file, noting any animals lost or censored from the study due to non-age-related causes, accidents, fighting, etc. Most of the parameters in Table 3 were usually reported in the studies in our dataset. However, we wish to emphasize a few noteworthy recommendations here. First, we recommend reporting the individual lifespans of all mice in all treatment and control groups, probably in a supplementary data file. This will enable other groups to perform extended analyses on the study findings. Second, to assess the effects of an intervention on early mortality, we recommend henceforth including the comparison of the lifespans at 90% survival between treatment and control groups. Historically, an assessment of the effect of an intervention on early mortality has not commonly been reported. When combined with lifespan at 50% survival, median, and 10% survival, maximum, these comparisons assess the effects of an intervention on the lifespan at different life stages. And the presence of an effect on one life stage without an effect on the others can offer potentially useful insights. One example is the effect of N-acetylcysteine affecting late-life mortality in males and not females, discussed earlier. Another example is one group of investigators in our dataset who failed to find a significant benefit of an intervention on median or maximum lifespan, but reported one on mean lifespan. It was apparent from the survival curve that early life mortality was reduced by this intervention, but that effect may have been overlooked had the investigators only evaluated median and maximum lifespan. Because mean lifespan is affected more by outliers than the other parameters, and because it does not indicate which stage of life was affected by the intervention, we recommend against using it. The age at which 90% of the rodents are still alive may be a useful measure of the effect of an intervention on early life mortality. This is the point in the life cycle of common lab mouse strains when the mortality rate is accelerating but has not yet reached its peak. Thus, a delay in the time until a cohort reaches 10% mortality will suggest that early mortality has been delayed by an intervention. It is perhaps debatable whether lifespan at 90% survival is the optimal point to assess early mortality in rodents. The exact figure might be decided among experts in the field, but it is clearly a more specific indicator of early life mortality than mean lifespan. Assessments of midlife and late life mortality, lifespans at 50% and 10% survival respectively, have been routine in the literature, and we have no modifications to suggest for assessing effects on mortality at these stages of the life cycle. Additionally, we suggest reporting these lifespan data with their exact p-values regardless of statistical significance. Routinely doing so may help normalize reporting results of intervention protocols having p-values above 0.05 and thereby encourage the reporting of studies finding no significant effects, which can also be informative. Moreover, consistent reporting of these data will enable sorting of aggregated results according to p-values. This capability might be of interest to investigators who want to choose the interventions with the highest likelihood of positively affecting their intervention groups, interventions with the lowest p-values, or who want to attempt to retest an intervention that displayed questionable effectiveness, interventions with p-values close to 0.05. To illustrate what most of our recommendations might look like if they were efficiently presented in a single table, we present Figure 2, which we call the Statistical Overview of Lifespan Intervention Data, or SOLID table. To create this table, we use the raw data from the investigation of the effects of rapamycin on mouse lifespan by source 27, which is a paper entitled Rapamycin but not resveratrol, or simvastatin extends the lifespan of genetically heterogeneous mice, by R.A. Miller and other authors in the Journals of Gerontology, Series A, Volume 66A, Issue 2, in February 2011, pages 191 to 201. We invite other researchers to consider using this table's format to summarize their future investigations. A copy of the original SOLID table in Microsoft Excel is provided in the supplementary data file for other investigators to use as a template for reporting their own findings in this format. Reliable access to these data in a standardized format across studies can facilitate rapid aggregation and comparison of many different interventions to evaluate the stages of life at which each intervention affected mortality. We are currently interested in collaborating with the authors of the studies in our dataset to obtain their primary study data so that our full set of data recommendations can be added to their respective entries in RAID. Finally, we have made our primary data table containing all RAID entries available with this manuscript. It can be found in the supplementary data file. Figure 2 shows the statistical overview of lifespan intervention data, or SOLID table. The species shown is a mouse. The strain shown is het3. The genetic modifications are none. The intervention is rapamycin at 14 milligrams per kilogram in food, and the intervention was initiated at 9 months. We see the lifespan data at X% survival in days for 90%, 50%, and 10% survival for both males and females. For N, footnote A states that this represents the number in each group, quote, at risk, end quote, after censoring up to that point in time. We see for the control group at 90% survival, 264 females, 331 males. At 50% survival, 249 females, 314 males. At 10% survival, 237 females, 309 males. And for the treated group, we see at 90% survival, 142 females, 161 males. At 50% survival, 130 females, 145 males. At 10% survival, 130 females, 145 males. In terms of lifespan, we see for the control group at 90% survival, 664 days for females, 503 days for males. At 50% survival, 891 days for females, 831 days for males. At 10% survival, 1,078 days for females, 1,061 days for males. And for the treated group, for 90% survival, we have 776 days for females, 543 days for males, 1,039 days for females, 890 days for males, 1,254 days for females, and 1,183 days for males. In regard to the difference in days, footnote B states this is calculated as treated lifespan minus control lifespan at each survival point. Here we see at 90% survival a difference of 112 days for females, 40 days for males. At 50% survival, a difference of 148 days for females, 59 days for males. At 10% survival, a difference of 176 days for females, 122 days for males. The difference as a percentage is described in footnote C as being calculated as the difference between treated lifespan and control lifespan divided by the control lifespan at each survival point. And here, at 90% survival, there is a difference of 16.9% for females, 8.0% for males. For 50% survival, there is a difference of 16.6% for females, 7.1% for males. And at 10% survival, there's a difference of 16.3% for females and 11.5% for males. Footnote D regarding the p-value states that the p-value is calculated using a one-tailed Fisher's exact test with 2x2 contingency tables, alive, dead, controls, and treated, for the proportion of the treated group alive at the given survival point for the control group in days. For example, for female controls at 90% survival, lifespan was 664 days, while at 664 days, 96.5%, a higher proportion in the treated group, were surviving in this investigation. And the p-values are for 90% survival, 0.0109 for females, 0.0565 for males. For 50% survival, the p-values are less than 0.0001 for females and 0.0894 for males. And at 10% survival, the p-values are less than 0.0001 for both females and males. Materials and methods. Our methods can be classified into two main project areas. One, PubMed queries and data extraction, and two, construction of our web-based data visualization tool. PubMed query design. All studies included in RAID had two main sources. One, the PubMed database located at https://pubmed.ncbi.nlm.nih.gov, and two, nomination by our colleagues. Our PubMed queries were designed to successfully identify a high proportion of studies reporting a positive effect on the lifespan of mice or rats relative to controls. Unusually short-lived strains were excluded, including strains used as disease models. Because the choice of words and phrases used to describe life extension investigations in the literature has varied considerably between investigators, our PubMed queries had to be complex enough to account for this variability. In designing our PubMed queries, we first combined synonyms for the rodents of interest, mice and rats, into a single query string. For this investigation, our PubMed query string was open parentheses mice open bracket TIAB close bracket or mouse open bracket TIAB close bracket or moose open bracket TIAB close bracket or musculus open bracket TIAB close bracket or murine open bracket TIAB close bracket or rat open bracket TIAB close bracket or ratus open bracket TIAB close bracket or norvegicus open bracket TIAB close bracket or rodent open bracket TIAB close bracket close parentheses. Note that TIAB in brackets is the PubMed field tag for querying only the title and abstract fields of PubMed entries. This query string was then combined using the AND operator with other query strings which use synonyms for the word lifespan, such as life-span, health-span, health-span, longevity, and others, resulting in a compound query which was then submitted to PubMed. Manual screening of the results followed, as described below. Each study in the search results was evaluated for relevance, according to its title. Retained studies were then evaluated based on their abstracts. Studies with an abstract suggesting a high likelihood of being relevant were retained for evaluation of their full-text manuscripts. The manuscripts were then read to confirm their relevance, rejected if irrelevant, and their essential data extracted if relevant. Extracted data was aggregated into the spreadsheet upon which the web-based data visualization tool was based. Not all studies reported mean, median, and maximum lifespan data, but most studies reported either mean or median lifespan data, and most reported maximum lifespan data. Data extraction. The data extracted from PubMed and the full-text manuscripts included the PubMed ID, PMID, of the study title, and bibliographic information, the intervention reported to be associated with rodent life extension, the type of rodent, mouse or rat, the strain of rodent, the sex of the group in which the effect was observed, the type of intervention, genetic, pharmaceutical, surgical, etc., the number of rodents in the control and treatment groups, the mean or median lifespans in days of the control and treatment groups, the percentage difference between the mean/median lifespans of the control and treatment groups, the p-values for the differences in mean/median lifespan between those groups, the definition of maximum lifespan used by the investigators if reported, the maximum lifespans of the control and treatment groups, the percentage difference between the maximum lifespans of the control and treatment groups, the p-value associated with the difference in maximum lifespans, and special notes about the study. This data was recorded in a spreadsheet with each row describing the comparison between one intervention group and its control group. Note that approximately 25% of the studies in our dataset apparently did not report exact lifespan data, so it was manually estimated from survival curves in those manuscripts. These estimations may be slightly different than the actual data. Construction of the web-based data visualization tool. The web-based data visualization tool was written in JavaScript and can be accessed at the URL https://levf.org/raid. Upon navigating to this URL, the software tool loads the entire dataset from the data spreadsheet into the client browser, which enables rapid searching/filtering without further network requests. The software tool visualizes each row of the data spreadsheet as a horizontal bar, with the length of the bar being commensurate with the magnitude of lifespan extension reported in the associated study. Bars are sorted in descending order based on the number of days of lifespan extension reported in each respective intervention group relative to its control group, and are color-coded according to the sex of the groups of rodents for convenient visualization based on sex. As a default setting, the bar chart is sorted according to the mean/median lifespan extension, but the user has the option to sort it based on the increase in maximum lifespan extension in days. Filters are provided to constrain the subset of the data displayed in the bar chart. Filters can be applied to the 1. Name of the intervention, case-insensitive substring match, 2. Sex of the rodents, 3. Age at administration, 4. Type of intervention, and 5. Number of rodents treated. Clicking any individual bar causes a table containing the study details, study title, PMID, authors, p-values, etc., to drop down below the bar. Abbreviations. AC5 stands for adenylyl cyclase type 5, GH stands for growth hormone, GHRKO stands for growth hormone receptor knockout, HAGR stands for human aging genomic resources, IGF-1 stands for insulin-like growth factor 1, PAPPA stands for pregnancy-associated plasma protein A, PMID stands for PubMed ID, RAID is the Rodent Aging Interventions Database, SOLID is the Statistical Overview of Lifespan Intervention Data, URL is the Uniform Resource Locator, and VEGF is the Vascular Endothelial Growth Factor. Author contributions. Maximus V. Peto designed the PubMed queries, performed the manual evaluation of titles, abstracts, and manuscripts, extracted and recorded relevant data from manuscripts, conceptualized the RAID data visualization tool, performed the statistical calculations, designed and created the tables, and wrote the manuscript. Anthony J. Floyd created the data visualization tool using JavaScript. Ben Zealley adapted the data visualization tool to be hosted on a public web server, enhanced its user interface, suggested additional functionality, created the RAID name and logo, and created the name for the solid table. Aubrey de Grey initiated the PubMed query and data extraction project on behalf of LEV Foundation for internal research purposes. All authors reviewed, offered feedback, and approved the final copy of this manuscript. Acknowledgements. We gratefully acknowledge Oliver Zollman and Caitlin Lewis for having nominated a significant number of studies relevant to this project. We also express appreciation for Meredith A. Olson, Alan Giacomo, and Caitlin Lewis for their careful review of and suggestions for this manuscript. Conflicts of interest. The authors declare that they have no conflicts of interest. Funding. LEV Foundation provided financial support for the initial PubMed query and screening project and for customization and web hosting of the data visualization tool. Long Life Labs, LLC, provided funding and personnel for the development of the RAID data visualization tool and the writing of this manuscript. Both Long Life Labs, LLC and LEV Foundation contributed equally to paying the fees associated with the submission, peer review, and publication of this manuscript. Now, we will show the references section of this paper. I will not read out the individual references, but there will be a musical section accompanying the presentation of the references. In the meantime, please feel free to post any remaining questions or comments, and we will make sure that the authors of the RAID paper receive any of the questions or comments that you may have. Thank you very much for attending this Virtual Enlightenment Salon, and I hope that we can all live long and prosper.